In this video, we're going to attempt to do a problem where an object is going to land at a different height than where it started from. And specifically, we have a boy throwing a rock towards a lake, and the distance from the base of the cliff where the boy is standing to the edge of the lake is given as 45 meters. So I've drawn my cliff, drawn my lake, and labeled the distance as 45 meters. As we read on, we realize that the cliff is 28 meters high. So I'm going to go back to my diagram here and label it as 28 meters. Now, the next bit of information we get to is that when the boy tosses the rock, it rises to a height of 2.3 meters above the height of the cliff. So I'm going to go back to my diagram, again include that information in there and label as 2.3 meters. We also know that the boy launched the rock at an angle of 23.3 degrees with respect to the horizontal. So again, I'm going to include that in my diagram. Now we move on and identify what this question is actually asking us. And the first thing that they're asking us is what the initial projection speed was. So in essence, what they're asking us is what was the initial velocity of that stone at the 23.3 degree angle. So in order to figure that out, we're going to need to know what the initial x and y velocities are. So I think it's pretty clear that you see a triangle there where we're looking for the hypotenuse and we're given an angle. I think to do this, what we're probably going to find to be the easiest is to determine what that initial y velocity was, and then once we know the initial y velocity, we'll be able to work backwards and use the sine function to figure out what the initial velocity or the hypotenuse of that triangle is. Given the stone rises to 2.3 meters above the height of the cliff, if we assume that the y velocity at the top there is our vf, we can assume that it's 0. So using vf squared equals viy squared plus 2ad, we're able to rearrange the solve for viy, again canceling out and saying that vf is 0, and plugging in the given information where our dy is 2.3 meters above the height of the cliff. We figure out that our initial y velocity here works out to be about 6.72 meters per second. I'm not quite ready to round off and consider sig figs here because I want to carry this answer through for a while. Now, if we go back to our initial question here about the initial speed at that 23.3 degree angle, I now have VIY as 6.71759 meters per second. I know that it's a 23.3 degree angle, and if I'm looking for the hypotenuse, I'm going to wind up using the sine function. Now VIY is my opposite, the VI is the hypotenuse, so again I'm using the sine function, setting my sine of theta equal to the opposite over the hypotenuse, and now I'll plug in some information and rearrange. So again, our angle is 23.3 degrees, our opposite side being the VIY at 6.71759 meters per second, and VI, so we rearrange it, so we're solving for VI, and let's see here what we come up with. Sine of 23.3, our initial velocity along that 23.3 degree angle winds up being about 16.98 meters per second. Now that we've finished that initial step, we're asked whether or not the rock reached the lake. And so, in order to figure this out, it really depends on how fast this rock was thrown horizontally. And it's also going to depend on how much time this thing is in the air. So the first of the two things that I'm going to determine is the VIX. Now if we go back to our initial trajectory, it's 23.3 degrees for the launch at 16.98 meters per second. We know the VIY worked out to be about 6.72 meters per second. I could easily use Pythagorean theorem to figure out VIX. So a squared plus b squared equals c squared, where I'm given sides a and c and I'm asked to solve for side b. The other way to do it is to use the tangent function. where we're considering the sides opposite and adjacent to that 23.3 degree angle. And that's the way I'm going to choose to do it here. So you'll see that I've put tangent theta equals VIY over VIX. I've rearranged it to solve for VIX. So VIX would be equal to VIY divided by tangent theta, and plugging in for VIY and tangent theta, we find that our VIX works out to be about 15.5981 meters per second. Again, I'm going to hold on to some of those extra digits there for a little while. Now, I mentioned before, it doesn't just depend on how fast this thing's moving, but also how long it's up in the air if we're to figure out whether or not the rock reaches the lake. So I'm going to break this time up, and I'm going to consider the fact that we have to maybe figure out how much time the rock is rising and then how much time it's falling. So I'm going to say that dfy equals diy plus viyt plus 1/2 at squared. But in order to solve for time here, you'll notice that I have two times in there. So it's not as simple as just plugging and chugging. We'd have to use a quadratic equation. So instead, because we don't tend to focus on that, I'm going to say that the total time equals the time up, again, plus the time down. So what does our time up depend on? If we're to solve for that, I think it probably has something to do with the motion in the y direction. So I'm going to choose to use VFY equals VIY plus AYT. Because I know the final velocity at the top is going to be 0, I can rearrange this and solve for time. So time equals negative VIY divided by my acceleration in the y direction, which is just negative 9.81 meters per second squared. So doing this, I find that the time up winds up being about 0.685 seconds. Now again, that only covers the upward portion of this object's trajectory. So now let's focus on figuring out how much time it takes to get down. So to figure that out, I chose to use the fact that I know how far this thing is going to have to fall in the y direction. So I'm using dfy equals diy plus viyt plus 1/2 ayt squared. Now thinking about it from the top, that initial displacement in the y is just going to be 0, so I can get rid of that. I know that if we're just talking about from the top down, that initial velocity in the y direction is also going to be 0, so this simplifies down to be dfy equals 1/2 ayt squared. Rearranging it to solve for t, I get t equals 2 times dy over ay, and I take the square root of that whole thing. Now let's plug in some numbers here to figure out t down, and we get t equals the square root of 2 times, well, the distance it falls from the top is now negative 30.3 meters, okay, because we had to consider the fact that it rose 2.3 meters above the height of the cliff. So plugging in, dividing by negative 9.81 meters per second squared, and then in the last step, taking the square root, I come up with a time down of about 2.485 seconds. So, our total time now, again, is our time up plus our time down. So we're going to add our 0.685 seconds plus our 2.485 seconds, and we find that the total time this object is in the air is about 3.17 seconds. So how far does this thing go in the x direction in those 3.17 seconds? Well, that's going to depend on the initial velocity in the x direction, which of course doesn't change because there's no forces acting on it in the x direction. So our initial velocity in the x direction is 15.5981 meters per second, and it's doing that for a total of 3.17 seconds. So I multiply my velocity in the x direction times the time, and I find that the dx is about 49.446 meters. So the question asked, does it reach the lake? Well, the lake was only 45 meters away, so yes, this object travels 49.446 meters.